So far in bimodal failure, we've seen three different examples of failure by open and failure by short for an individual component. In all of those three examples, we have tried to protect against failure by open and failure by short by placing two of the components in series or two of the components in parallel. On this slide, we generalize that and we consider placing n components in series or n components in parallel. So first of all, here is the notation associated with each of the n components, which can fail by open or fail by short. P sub I is the probability that component I is functioning. Q sub I O is the probability component I has failed by open, and Q sub I S is the probability that component I has failed by short. And all of these are at a particular time t0, for example, 1,000 hours. The first thing we're going to look at here is a series system of n mutually independent components. So the independence assumption is still in place. Now you're used to seeing R here in the past as R of P, but because the notation gets a little bit clunky when you throw in all of these three different probabilities, which of course have to sum to 1 because you are in one of those three states, either functioning, failed by open, or failed by short, we simply take R and drop its argument. But R is still the probability that the system functions, and this is more easily computed by taking the complement of that and saying this is equal to 1 minus the probability that the system fails. Well, there are two different ways that the system can fail. The system can fail by open, and the system can fail by short. So that is this step right here. The next step says the probability that a system fails by open means that one or more of the components fail by open when you have a series system. The way that the system fails short is all of those components have to short. So this is going to be the easiest one to see. How do you get the probability that all the components fail short? Well, you simply multiply their probabilities of failing short, and that's this term. When you have the situation where you're trying to find the probability one or more components fail open, instead of multiplying, you take 1 minus the product of 1 minus the probability of failing by open. You'll notice that the 1 minuses cancel here, and your final solution for the series system will be this quantity right here. When you go to a parallel arrangement of components, and once again these are mutually independent components, you have exactly the same setup as before. Here are your three probabilities. Those three probabilities sum to 1 for each of the n components, and they are all stated for a particular time t0. So in this case, the system reliability is the probability the system functions. Once again, we calculate the probability that the system fails. So that's the probability the system functions is 1 minus the probability the system fails. This system can fail by open or can fail by short. So those two get added in and the negative gets distributed across. How does a system fail open? It fails open when all of the components fail open, and for the parallel system, you're just going to multiply the open probabilities. The other possibility is the system fails short, and that is the probability one or more components fail short. That is this quantity right here. Once again, the ones cancel right here, and you are left with this expression right here as the system reliability for a parallel system of n components who have two different modes of failing, failing by open and failing by short. Back in 1964, in one of the very early reliability books out there, published by Prentice Hall, they spend a good 10 or 11 pages here on looking at optimization. And what they're trying to do is they're saying, look, if you have a series system of components, and we did that 2 slides ago, and you make the further assumption that all of those components are identical, then their question is, what is the number of components? In other words, they want to find the number of components n that maximizes this quantity right here. Where did we get this quantity right here? We went back 2 slides to the series system, and we simply made all of the components identical, and when you do so, you get this quantity. Well, how do you find a maximum if you want the highest system reliability? You differentiate this quantity with respect to the unknown, and the unknown is n. So when you take a derivative, now notice that n is up in the exponent, you get 1 minus q0 to the n, that's just this first term, times the natural logarithm, and that's given by log here in the slides. In the book, it would be given by ln, minus q sub n to the s power multiplied by the natural log of q sub s. Now, when you take this second term over to the other side of the equation, you can see if you take the log of both sides, your n will get pulled down. So with 2 or 3 steps of algebra, you'll see that this quantity right here is the value of n, which makes this derivative equal to 0. So this tells a design engineer, if you want to maximize the system reliability, this is the number of components that you should place in series in the bimodal failure setting.